Very good afternoon to all of you. So today we will be having our second webinar session as part of our Cadence Tech Talk series. So we already did a first Cadence session last month in March. So this is our second part of our Cadence Tech Talk series, which is the stage 1-2. So just would like to know if you all can hear me clearly. There might be a bit of noise from my side here, so just want to know if you can hear me loud and clear. If you can hear me, do type yes on the chat box so that I know that I'm audible from your side. Okay, I do receive a yes. How about the rest? Can you all hear me? To all the attendees, am I audible to you? Okay, I hope it's clear because there might be a bit of noise from my side. There's some minor repair work going on. Other than that, okay, yes, okay, I do see that. I do see a lot of reply from you. Thank you very much. Okay, so my name is Julian. So I will be presenting I will be presenting the Cadence front end design part. So before I start, let me allow Ice to give the opening.
Thank you, Julian. So this is Ice. I'd love to give some opening for this part. So as you already see in the information board, so for the certificate, as we already closed the session one in last month, so we already sent out the certificate. Anyone you didn't receive the certificate, please reach us at the email eventc@cadence.com. So please help to send us if you didn't receive it. And for the opening, so this is the page. Last time I also do the opening. So in this month and in today, so Julian will help to provide the front end design and also part of the IC part. So he will give you the description about the synthesis and also some other front end tools. Thanks, Julian. So please take over.
Okay, thank you, Ice. Okay, so once again, very good afternoon to all of you. It's good to have you all here again. Good to see some repeating participants from the first session. Okay, for those who are new to this session, so this is actually our second Cadence Tech Talk, which we had an earlier Cadence Tech Talk in March, where we talk about the digital design flow, the full digital design flow. And today in this month of April, we are going to talk more on stage 1-2, which is the basic introduction of Cadence digital front-end design technologies. We're going to talk more on the front-end design part, the earlier stage of the digital design flow. Okay. Before I start, let me do a video check. Okay. Okay. Okay, so as my introduction, my name is Julian. I'm a digital FED engineer from Cadence, Singapore. Okay, so for this webinar today, which is from 3:30 to 5:30 Singapore time, it will be the topic on the digital front end, and there is a prerequisite for this webinar, which is held on March, which is the prerequisite for this webinar is actually the introduction to Cadence digital full flow. So if you have attended the March webinar, you'll be able to understand on the full flow of the digital design. So the agenda for today's session will be 1 hour on the logic synthesis topic, where we will talk about how our Cadence tool, which is Genus, does the logic synthesis. And then the next 30 minutes, we'll talk a bit on physical synthesis and also some other topics like LEC and DFT. And then for the final 20 minutes, we will do a live Q&A, where you can submit your Q&A questions into the Q&A box. So there is a Q&A box here. in your Zoom session. And if you have any questions while I am presenting the slides, you can submit your questions in the Q&A box. So our expert panelists, which is Rian and Hui, they are also in this Zoom session now. They will answer your questions during the presentation. So submit your questions into the Q&A box, and then they will be answering your questions. And if there are any unanswered questions, we can answer it later through the live Q&A in the final 20 minutes of this webinar. Okay, at the end of this webinar, there will be a survey form. Okay, survey form for you all to fill up on at the end of the presentation. Okay, so for any questions on the certificate and so forth, you can send an email to the email that ICE had shown just now.
Yeah,
if not, you can just submit the question again, and Bian and Hui will help you to answer. Okay. Yes, ICE?
Yeah, so the email, I repeat again, it is the event underscore SEA at cadence.com. So maybe Julian, later I can send you the slides and you can show it in the last page, or maybe
Okay,
after
okay, sure.
presentation. Yeah,
okay.
Thank you.
Okay, without further ado, let me start on our slides today. So just a refresher on what we talked about in March. Okay, so as you know, the basic digital design flow that we have can be separated into three main phases. Number one is the system phase, where we develop the spec for the design. And then the next phase is the logical phase, where we develop the RTL and synthesize the RTL to logic gates. And then the last phase is the physical phase, where we do floor planning, placement, and routing. So three main phases in the digital design flow. Okay, today we are going to talk about the logical phase, only the logical phase, where the main topic is about logic synthesis, about how we generate the gate level netlist from the RTL. Okay, so we already created the design spec, coded the RTL. Okay, so today we are going to talk about the logical synthesis. Okay, well, this is another diagram of that we showed in March, which is the full digital design flow implementation. And today's topic, we're going to focus on this logic synthesis step, where we convert the RTL into a synthesized gate level netlist. And how Cadence do it is that we have a solution, we call it as the genus synthesis solution. So this is the name of the tool from Cadence that is used to do logic synthesis. And this is what we're going to talk about for the next 1.5 hours. Okay, so the main topic is about genus logical synthesis. And if you have used it before, or if you're new to it, let me just give you a refresher. Okay, if you want to start the genus tool, all you need to do in your Unix and Linux environment, you just need to type the command genus, and the genus tool will be invoked, provided that you have all the licenses and so forth. So how do you invoke genus? You just go type the command genus, or you can just do a genus-f run.tcl and -log genus.log. So what it does is that when you just a -f, it means the file name that is going to be sourced once the genus is invoked, once the genus tool is invoked, and everything that is running throughout this whole genus command prompt and so forth, they will be logged to this log file called the genus.log. Okay, so it's a very simple command to invoke the genus synthesis tool. And then before I go on to in-depth of the whole environment and so forth, let me just briefly inform you the basic setting and querying command of a genus. So we have two main commands. One command to set the attribute. We call it as setDB. SetDB, set the object that you want to apply the attribute to, then you set the value. Okay. And then the other command, if you want to retrieve the value of an attribute, you just do a getDB. So throughout the slides, you're going to be seeing a lot of setDB and getDB commands. So just to let you know that setDB and getDB are commands to set an attribute or set a value, and getDB is the command to retrieve the value. Okay. Okay, so this slide here shows the basic genus synthesis flow. Okay, the basic flow of what is going on during logical synthesis. Okay, so you're going to see, like, for instance, the first step is about setting the technology library. Then you read the RTL, and then do elaboration, and then do init design, and then read the constraints, apply optimization directives, and then do the synthesis, okay? Run the synthesis command. And then finally, of course, when everything is done, you have to do a reporting, analyze the reports, write the output files, and then if constraints are being met, you proceed on to place and route. If it's not, you just redo everything again. Okay, you change, you modify the optimization directives and so forth. Okay, in summary, you just have to remember for most of the flows that Cadence has, okay, it's all always relates to the first thing is always about setting up your input. Okay, reading in the RTL, which is your input. Then you set up your optimization directives. How do you want to optimize? You want to optimize for timing, area, power. And then next, the main command, which is to synthesize. And when everything is done, you write the reports, you write the netlist, and that's done. And then you go on to the next phase of your digital design flow. So what's the next phase after logical synthesis? Is the physical phase. Okay, after the logic synthesis, the next phase is physical phase. Okay, we're going to go one by one on each step. Each step we're going to go on, and then I'm going to tell you what each of these steps do. Okay. Before I go on, just want to briefly describe what is the inputs and outputs of a genus synthesis flow. Okay, the inputs and outputs are very important because, of course, inputs, you need to have all these available inputs to do a correct synthesis, and outputs are the files that is being output by genus synthesis. So those are the files that you will be passing on to the next phase, which is your physical phase. So in a very simple description, the inputs are your RTL, your SDC constraints, all your clock definitions, your library, your cell library, logical libraries, timing libraries. We won't talk about power intent today, so I'll just put it's optional. We'll not talk about this. And then if you are going to do physical synthesis, you will need some physical information in the form of left, depth, QRC type file, and so forth. Okay, these are all the inputs that you must have before you start to do your logic synthesis. And then, of course, once you're done, okay, all the outputs, you need to be aware of what's being output from your tool. What the main thing that's going to be output from your logical synthesis genus tool is your optimized gate level netlist. And there are all other outputs that will be used for verifications or for your next phase of design flow, which is the physical phase. Okay. Okay, so now we'll talk about the first step in the logical synthesis flow, which is setting of the technology library and initial setup, okay, which is actually your setup of your inputs. Okay, the first input is your input library. Okay, you must have this to do a logical synthesis. Libraries can be divided into two different types of libraries. One is a logical library and one is a physical library. Okay, so your logical library contains the functionality, the function of each of the cells in the library, the timing, power, information of the standard cells. So it must contain the functionality, the timing information, and the power. How much power for this AND gate? How much timing? How much time does this? How much delay does this AND gate takes? All this information must contain in your logical library in the .lib format. And then you must also have the physical libraries, which contains the abstract view of the layout of your standard cells and macros. They are in the .lab format. What is the shape of your AND gate? What is the shape of your OR gate? All this, what is the area of your OR gate? All this information is stored in the physical library. So you need to provide a search path for the tool to where to find these logical libraries and physical libraries. Okay, the command will be by the setDB. I mentioned about this one, the setDB command. Set your search path to where to find your logical and your physical libraries. Once you have defined your logical libraries and the logical library path and your physical library path, the next command is to read the libraries. Okay, let's say you have three libraries, three 0.9 1 volt libraries. Okay, then you just need to read the libraries into the genus. Okay, and then it will store the information into your genus database. So once you have read the libraries, all your AND gates, OR gates, functionality information, timing information, power information, once you've stored all this, read all this, then you can start to tell genus what are the libraries that you want to use and what you don't want to use. So this is a command where you say, you tell Genus, you set dB. I don't want to use any cells that is bigger than 16 drive strength. So you set dB, anything which is D16, you set it, don't use the true. Okay. So this is how you control what are the logic libraries to use for synthesis. And then the next command is to read your physical libraries. So you do a read physical dash lefts. So you read all the physical information of your libraries, your area, your dimension, and so forth. Okay, so once you read the library, once you read this left, right, it will automatically enable this physical layout estimation algorithm in Genus. Okay, we call it as PLE. Okay, so what it is that Genus needs to model something, needs to model the timing information and so on. So it's actually a physical modeling technique, okay, used by Genus. It's a physical modeling technique that uses the tag information and cell information from left libraries, okay, for the tool to do accurate, to have some sort of like a physical information much earlier at synthesis, to do logic synthesis much better in a more accurate manner. So they call it as a PLE, which is the physical layout estimation, and it will be automatically turned on once you read the physical libraries. Also take note that if you are reading in the left, we also recommend you to read the QRC tag file. Okay? The QRC tag file contains RC information of the technology of your design. Okay, it contains RC information. So this also increases the accuracy, the physical accuracy of your logical synthesis. It will be very useful later on when you're doing physical synthesis. Okay, so we already talked about reading the logical libraries, then we talk about reading the physical libraries. And then this is the summary of the library files that's going to be used by Genus. Okay, we will not recommend like Violet model. What we mean by Violet model is you just read the topic. Okay, we don't recommend this. Instead, we recommend you to read the lib as well as the left files. Okay, because by reading in the left files, the physical libraries, you are enabling the PLE inside Genus, and this increases the accuracy of the Genus synthesis and accuracy in terms of the correlation to the physical phase. You need to have a correlation to the physical phase. So you want to increase the correlation to your physical phase. We recommend you not to use Violet model, but to read the left files so that Genus enables the PLE engine. Okay. All right. And then if you are going to do Genus physical, okay, we will recommend not only the lib left, you also need the floor plan depth file. We'll talk about this much later on when we talk about the physical synthesis. But even for now, even for the synthesis, the basic synthesis, do not do Violet model. Instead, read the .lib and read the .left so that you have a PLE engine enabled in synthesis. Okay, next I need to talk about this MMMC. Okay, this MMMC is a very important topic because in today's IC design, IC design now today, they need to operate in different modes and different corners. They're no longer talking about only operating one mode and operate one voltage. Nowadays, your IC design need to operate in 1 volt, 0.5 volt, 0.6 volt. Okay, and you also need to operate in functional mode, test mode, and several other input-output functions. There are many, many different modes. So when we are synthesizing a design, you want to synthesize, you want to optimize a design to meet different modes and different voltages. That is why we have this concept of multi-mode, multi-corner. When you are doing logical synthesis, the synthesis need to be doing optimization on different modes and different corners, meaning at different functional modes, test modes, and at different PVT corners, different voltages, different temperatures, because your IC design is going to be operating at different voltages. So all these need to be done concurrently. Okay, we're not doing serially. We are optimizing all these modes and all these corners concurrently. So in order to enable multi-mode, multi-corner, multi-mode, multi-corner, we not only need to just read left and just read lib. It's not just it's not a simple command. We need to write out this MMMC file. Okay, we need to write out this MMC file so that the tool can read it. Okay, so when we're creating this MMC file, there are 8 steps here. So I'll briefly go through all these 8 steps. Okay, in summary, right, the MMC technology, which is very common nowadays, it enables concurrent analysis and optimization of different views. Okay, so there are 8 steps. I will very briefly go through each of them. The very first step is create a library set. Okay, this is the MMC file. Okay, the MMC file contains a bunch of commands. Okay, but all these bunch of commands can be summarized into 8 steps. 8 categories. Okay, so the first step in creating the MMC file, you must create a library set. A library set is just a very simple create library set command. What it basically does is create a ticker list of libraries. If you have 5 libraries, you create a list of 5 libraries, and then you give a name to this set. You call it as a library set. Just give a name to this library set. And then you have another 5 libraries, which is at a different voltage. Then you create a ticker list of that library, and then you create a library set name for it. Another set of libraries at different voltage, and so forth. Okay. So the first step is create a library set. Once you create a library set, the next step is create an operating condition. Here you are just defining an operating condition name. Okay, an operating condition. So you use the command create opcon. It's just create the name of an operating condition. Let's say your design is running at 3 different voltages. So you are just defining the 3 different voltages: the 1.08 volt, the 1.32 volt, and the 1.25 volt. You're just defining the name for these 3 operating conditions. Once you have defined the operating condition now and the library set, this is where you merge them together. You're merging them together and creating a timing condition. Okay, so the command is create timing condition. So remember I mentioned that you have created a library set for the 1.0 volt libraries. You have created a library set for the 1.32 volt libraries. You have created a library set for 1.25 libraries. So now you're just merging the library set with the operating condition name. That's it. Okay, so in summary here, create timing condition equals to merging your library set with your operating condition. That's all. That's all for this third step. Now, the next step is about creating an RC corner. So the RC corner, there are C words, RC words, different RC corners. So the create RC corner is just to create and name an RC corner. That's it. That's all you need to do, is just creating an RC corner, which will be used for delay corner later. And then next is creating the delay corner. Okay, so now you already create library set, create opcon, create timing condition, create RC corner. The next step is merging all of them again. You're going to merge all of them again. And the merging of all those items above is called a delay corner. This is called a delay corner. Delay corner is basically merging your RC corner, which is whether you have RC versus C versus, okay, different RC corners for the RC estimation, the resistance and cap, different RC corners. You're creating a delay corner. Okay, in the components of the delay corner is your RC corner and the timing condition. Okay, remember your timing condition is actually your library set and operating condition. Okay, so these are all just standardized steps, but it's all done serially, one by one. Create something, merge it. Create something, then merge it. So the delay corner is actually a merge of your RC corner and your timing condition. Now you already done all the above already. Next, you create a constraint mode. Remember, we talk about functional mode, test mode. What's the frequency at 1.08 volt? What's the frequency at 1.32 mode? You have to create constraint modes for every different modes that you're operating. Okay, so you're also just defining a constraint mode, and then you use the SDC files associated mode. So you can see when you create constraint mode, the name of the constraint mode is functional WCL slow, and then the SDC file contains all your design constraints. What is the associated SDC file to your constraint mode? So here you're just creating constraint mode. You're still not doing any merging yet. You're just creating a constraint mode. Okay, and then the last one, no, almost there. Okay, we're not there yet. Still at step 7. Is where you are doing the next round of merging. So you're creating an analysis view. This analysis view is an important concept. We always use it. Analysis view. So analysis view is where you are merging your delay corner, which you have merged a lot of things above, with the constraint mode. So you're merging these two together in the end to create one analysis mode. Okay, now you have an analysis mode that has your RC information, that has your library information, that has your operating condition information, that also has your SDC information. So one analysis view contains a lot of information. And then finally, you do the set analysis view. So set analysis view is to tell the genus tool, I want to activate this analysis view for setup and this analysis view for whole optimization. Okay, that's basically the, the final step. You're activating the analysis view. You created a bunch of analysis views, 3 or 4 analysis views, but you only want logical synthesis to work on 2 for setup, 2 for whole, and then another one for power. Okay, for example. Okay, so you have done all the 8 steps to write out this MMMC tickle. Of course, once you've written it, it's just a file. Okay, you need to store it into genus, so you use the read MMC command to read the MC file. That's it. Okay, in this slide here, one very important thing I want to talk about is when do we do read libs and when do we do MC. So if you're just doing a single corner, let's say it's just one voltage, one constraint mode, just a very simple one corner. You don't need to do MMC. You just do like read library, just a very simple command, and then read constraints. Simple command to do the single corner. But if you are doing multi-mode, multi-corner, you need to do the read MMC. Okay, that's the main difference between a single corner run and a multi-mode, multi-corner run. How do I hide this? Okay. Okay, so let me refresh. So inside the basic synthesis flow, we have only talked about the very first step, which is the library setup step. Okay, next we'll talk about the reading RTL and so forth. Okay, next you've already defined your libraries, whether it's single corner or MC corner. So you have already defined your libraries, constraints, RC corners, and so forth. Next, you need to read the RTL. So in order to read the RTL, you need to define where's your search path. Okay, the path to search for your RTL files. And the command to read your RTL is read HDL. Then the files or RTLs that you need to read, what is the language of your RTL files? So basically the read HDL will load one or more HDL in the order given to memory. Files containing macros should be loaded before the macros are used. And then last one is if you do not specify any language, by default, you will use the V2001 language as your default. Okay, so here we talk about the main command to read RTL file. Remember, you have coded the RTL file, okay, and then you've set up your libraries. Next, you need to read your RTL, so you use the read HDL command to read your RTL. After you have read the RTL, you need to elaborate your RTL. You need to link all your designs and so forth and everything. You need to make sure that the genus understands the RTL that you read in. So what it does, what's the command to do that is elaborate. Elaborate is the command to is the next command after you read the RTL. What it does is that it will build the data structures and infer registers. It will do some date code removal, codes that are not needed, never used in the design. They will remove it, and then they will identify clock gate candidates. Identify if any registers they can do clock gating. Okay, this is where it's being done. It's done at the elaborate step. So elaborate is to elaborate the top design. Okay, if you have any questions, feel free to type into Q&A box. Our panelists, expert panelists, Hui and Rian will be answering your questions. Okay, I need to talk about these chipware components because since we're talking about elaborate, just to let you know, after you read the RTL and then elaborate, you need to know that genus comes with a library of reusable designs. Inside this genus tool, there contains a library, a lot of libraries of reusable designs. We call it chipware. Okay, these chipware components, they are proprietary to Cadence. So what's inside these chipware libraries? There are the common combi and sequential components. They have the arithmetic components like the adders and multipliers. They also have the memory components. Take note, these are not standard cell libraries. These are the architectural components. Okay, the data path structures. Okay, that is used when you are reading after you read in the RTL. Okay. So when you read the RTL, so how Genus does is that you will either infer the chipware based on its understanding of the RTL, or if you have coded the chipware inside the RTL, it will straight away instantiate that chipware itself. Okay, if you code the chipware into the RTL, all right, automatically Cadence will just instantiate that chipware into the design. Okay, so chipware components, they have multiple architecture implementations. Some chipware is good for, some architecture is good for timing, some architecture is good for power, some architecture is good for area. Okay, and there are multiple architecture implementations in these chipware components. And synthesis will pick one according to the need of the design. Okay, when synthesis is running, later on we'll talk about it. When synthesis is doing synthesis and so forth, right? That's where it will pick one that's suitable for a design. If your design is timing critical, it will choose architectures that are good for timing. And just remember, chipware is proprietary to Cadence, and they are already there when you have the Genus tool. It's already stored in the libraries. Okay, so now you've already read the RTL, elaborated it. The tool now Genus understands your RTL very well, links everything together, and then there's a top design now, and there are also sub designs. So one thing before you proceed, please run a check designer. Okay, we have a command called check design. This check design is very important. Basically, it does what the command says. It checks your designs. It needs to make sure that you do not have any unresolved instances, instances that are not linked, instances that they are just not being used anywhere, and it's not there's a linking issue. Okay, some missing instances and so forth. So the check design is very useful for that. It also checks other things like any undriven, any unloaded pins and so forth. So the check design is a very useful command to check your design right after you read RTI and do elaborate. So make sure you do that and review the log file warnings. And if you have any warnings or errors, please fix the issue before you proceed. Do not proceed if you have a lot of check design unresolved issues. So resolving all design references is very important. Okay, once you are done, you need the next step you need to do. Your check design is passing, everything is clean. Now you need to do one command called the init design, initialize your design. Okay, why you need to do the init design is the init design will help you to do the loading of all the libraries for each active analysis view, load the SDC for each active analysis view, and load all the RC corners. All those things that you have defined in the MMC, right? Init design will help you load all this information and link it to the design. Because when you first do your read MMC, you are only reading in the file. Then after that, you read your design. After you read your design, and then you read the MMC, you need to link these two together. Everything that you've defined in MMC need to be linked to your design. Okay, that is where the init design purpose is. The init design purpose is to link your design with everything that you have defined in the MMC article. So that is why the initialization design is very important. After a design has been initialized, the design initialized with everything from the MMC, the design is ready for execution. Okay, just to add on, I know that we're on this topic of specified design constraint. I know that why are we talking about design constraint? Okay, because design constraints are already read in by MMC, right? So why do we have these read SDC commands? So this is usually for single corner runs. Remember, single corner runs, we only read the libraries. Okay, so for single corner runs, you also need another command to read your constraints. So the read SDC command is to read the SDC files. Okay, it's usually used for single corner runs. So after you have read the SDC, do a check, make sure you check for errors, and then you also can do the check timing intent to check your SDC constraints, whether they are consistent with your design. Remember, we have a check design command, so we also have a check timing intent command. So the read SDC is useful only for simple usage, but not for MMC. Read SDC is just used for single corners. Okay, you might be running Genus on single corners, so this is useful for you. Okay, so let's check. So we have talked about read MMC, read HDR, elaborate, init design, and read SDC. So this top part, we have already talked about it. So now let's do a test your understanding part of the webinar. Okay, so I'm just going to pose some questions and please do answer it. Try to answer it. You can answer it by using the chat box. Okay. So the very first question is, What is the command to check for unresolved instances? Yeah, please type your answer into the chat box. What is the command to check for unresolved instances? It's a command that starts with check. So how do we check if there's any resolved instances? Remember, we have already read the design. Okay, you want to make sure that your design, all your instances are resolved, is able to link. So how about what's the command to check for unresolved instances? Anyone? Okay, I'll just briefly go through this one now. So the design to check for unresolved instances. Oh, there's an answer. Yes, correct. Thank you very much, Chartpol and Farm. So thanks for your answers. Yes, correct. Check design is the way to check for unresolved instances. Very good. Thank you. Thank you so much for the answers. Okay, then the next question is, if there are several top levels in your RTL, how do you define the top level design to be elaborated? Okay, there should be only one top design. You cannot have multiple top designs. But if you want the tool to be sure on the top design to be elaborated, what is the additional option that you need to add to your elaborate command to define your top level design? Okay, when I see an answer, init design, no, init design is yeah, good try. Init design is not the it's not used, it's used later on, it's not used for elaborate. I'll talk about init design later. Okay, yeah, elaborate is the correct command, but if you want to make sure that you are elaborating on the correct top design, you do a elaborate top design. You define your top design name here. Yes, very good. Yeah, elaborate top, correct. Correct, Farm, yes. So you do an elaborate top design, and that will be you will make sure that that is your top design and the rest are all sub-modules. Good. The next question, what is inside an MMC file? Yeah, so I'll just go through this quickly. So the inside MMC file, just remember, full set of timing libraries, constraints, operating condition, timing condition, RC corners, delay corners, and associated analysis views. Okay, it's a lot of information, but main thing is to define your analysis view with multi corners and multi mode libraries. Okay, what's the command to read an MC file? How do you read an MC file? Yes, when correct. The command to read the MC file is read_MMC. Okay, yeah. So just now we are all the reading of the RTL and elaborate is to define your. You need to elaborate the top design first before you go on to the next, which is the init designer. Okay. So now do you need to run init design for single corner runs, non-MMC runs? Do you need to run init design? Okay. Do you need to use init design for non-MMC runs? Let's say if it's just a single corner, you need to use the read MMC command. Okay. No, right? Correct. Yes. Chapo, yes, correct. No, you don't need if it's just a normal single corner run, no need to do init design. Yeah, just init design is only required if MC file is read. And do you need to use read SDC for MMC runs? Okay, another question of whether need or not. Okay, so do you need to use read SDC for MMC runs? So if you're doing a multi-mode, multi-constraint file, right? Do you still need to use read SDC? Okay, yeah. Okay, so okay, actually the answer is a bit actually, okay, the general answer is actually no. Okay, no, okay. You don't need to use read SDC for MC runs because constraints are already specified in MC file using create constraint mode. So you don't need to use read SDC. Read SDC is usually for single corner runs. Okay. So no, for multi-mode, multi-corner runs, you do not need to use read SDC because SDCs are already defined by the create constraint mode command inside the MMC file, so you don't need to do that. So just be aware of that. Because when you do your init design, right, you read MMC, and then you do your init design, all your SDCs are already loaded in. So you don't need to do another round of read SDC. Read SDC is only for single corner runs. Yeah, I hope this is clear. So if you have a follow-up question, do type into the chat box. Okay, Swan, thanks for your answer. Okay, so let's go on. Let's move on to the next. Okay, now we're going to talk about something a bit more interesting, which is the optimization part. How logical synthesis is optimizing the design, and what are the different recipes and so forth. Okay, so first thing, when you're talking about the when you're talking about the path groups, right? Sorry, when you're talking about logical synthesis, right? We need to talk about path groups. Path groups is a very important concept when we talk about timing optimization. Okay, okay, path groups. What are path groups? Okay, so it allows you to group different timing paths into a group called path group. Okay, what I mean is that different timing paths, for example, register to register, register to I/O, register to SRAM, SRAM to register. These are different timing paths, and then you want to group them into path groups. Why we need to group them in path groups? Because Genus optimizes on a course group basis. Okay, they will optimize, they will work on a group one by one, work on this group, the next group, this group, this group, this group. Okay, so that is very important for optimization. So by default, right, Genus creates separate course group. If you don't do anything, right, automatically when you create a clock in your SDC, right, Genus will automatically create different groups for each clock. Each clock will have their own group, and then Genus will calculate what is the target slack, target timing to be achieved with path groups for each clock group. Okay, they will optimize based on each clock. Clock 1, clock 2, clock 3, they will optimize clock 1, then after optimize clock 2. That's how they optimize. Okay, but if you don't want this to do this, right, you don't want the tool to optimize based on clocks, right? You want the tool to optimize based on resh to memory, based on timing paths, right? Then you can use the define course group and the path group command. Okay, for example, in here, I am creating a course group called clock resh to resh. So, and then I'm creating a group path. Okay, I'm defining a course group called clock resh to resh with a weightage of 10. Okay, to tell the tool add weightage of 10 to this. I want you to focus on this 10 times. Okay, let's say for example, and then focus on optimizing this path. We will weight 10. Okay, when the rest we will weight of 1 ignore it, but 10 I want you to put more emphasis on this path. And then after that, you create a group path. Where's your from point and where's your to point, and then associate to the course group that you just defined. Basically, the commands you can find from the documentation, but the main idea that I want to pass on is the concept of course groups. Genus will optimize timing based on the groups that you create. Okay, they will optimize if you don't define, they will optimize based on clock 1, clock 2, clock 3. But you can also override these group paths by creating group paths for resh to resh, resh to I/O, resh to memory, and so forth. Okay, there's 2 questions here. What other path groups can you think of? Okay, yeah, you can type your answer if you have an answer. What other path groups can you think of that you can create? I've already mentioned one example here, which is resh to resh. Any timing paths from register to register, I give them an importance of 10. Okay, so what other path groups can you think of? Anyone? You can type it into the chat. Okay, I'll just go through this one. Okay, what other path groups can you think of? So I can think of into register is one path group. Any timing paths from input IOs to register, any timing paths from register to IO, any timing paths from clock gates. So I will create all these group paths, and then then Genus will automatically I will optimize this timing, optimize the timing for this group, and then optimize the timing for this group, optimize the timing for this group, optimize the timing for this group. So they will optimize based on the importance of each of the path groups. Okay, and then after that, what weight would you apply on them? What's the weightage would you apply? I will apply a high weightage of 10 to register because if your design has a lot of flops, right, there will be a lot of register to register timing paths. So register to register are basically the most important, one of the most important timing paths in your design. But so I would say I would put the highest weightage for register to memory paths, memory to register paths, and to clock gate paths. And I will put lesser emphasis. I will tell Genus to put lesser emphasis by setting a lower weight to in to reg to out, into out, all those that interface with external. I will put it as a lower criteria first. Okay, because not only you're optimizing it, the other external party is also optimizing. So you've got two sides who are optimizing. So it's a bit not so critical, but the most critical one you need to take care is all those paths inside your own block. Inside your own block, they are the most important one because no one else is optimizing it for you. You are the one optimizing it for yourself. So all those internal timing paths, you must put a higher weight. Okay, I hope this is clear. If you have any question, please submit to the Q&A box. Okay, so we already talked about the concept of path groups. Next, there are also concepts of timing constraints. How are you constraining your design? There's the concept of path adjust, where you can actually tighten or loosen the timing constraint on a set of paths. Let's say register to register, I want to make it more pessimistic by 100 picoseconds. So I can use path adjust to make it more pessimistic. I can also make the paths to be less pessimistic by giving it additional optimism of 100 picoseconds. I can tighten and I also can loosen. So I use the command path adjust to do that. There are also others, set multi-cycle path, set clock uncertainty, set clock latency. Multi-cycle path, I won't talk about it, but I'll just talk about set clock uncertainty. Set clock uncertainty is basically specify clock guard band for each of the clocks. Okay. Sometimes when you define a clock, you need to add a bit of guard band to it. I won't talk about this. I won't talk about latency, but I'll talk about these three things here. Okay, set max transition and set max fan out and set max capacitance. Set max transition basically tells Genus that when you are selecting the logic gates, right, make sure that they can meet a transition of 50 picoseconds. So make sure that you are not using low driving cells, use high driving cells so that you can meet the transition requirement. Max fan out basically says that for all my logic gates that you are going to select and then the net connection and so forth, make sure that you don't exceed the maximum fan out. Usually people will put a maximum fan out 32, 24, 12, or they make sure that if for every cell, make sure you don't drive anything more than that. You drive anything more than that, what will happen? Right, you will have timing issues. You might even have congestion sometimes. And then capacitance. Capacitance is a loading. Make sure that when you are deciding on which logic gate to use, do not select a cell that cannot meet the femtofarad, the capacitance, the loading of the loading pin. So these are the constraints. These are the constraints that the tool must meet when you are synthesizing a design. Okay, got it. So the first one is create course group so that they tell the tool what are the groups to work on. Second one is telling the tool what's the transition limit that you must meet, what's the fan out limit that you must meet, what's the capacitance limit that you must meet. Okay, all these are constraints to help synthesis to optimize your netlist. Okay, next one is ungrouping. You might or might not have heard of ungrouping. Okay, let me explain this ungrouping. So in other words, first of all, if you hear anything about ungrouping, make sure you do not prevent ungrouping unless you have a good reason. So ungrouping is actually a synthesis methodology. When you are reading in your RTL, you have different modules. Okay, all these modules, they are all hierarchies. Okay, but sometimes you can ungroup them. You can mix two modules together, ungroup them, flatten them, and optimize them together. Okay, because otherwise they'll be bounded by the hierarchies. They have boundaries. So we are ungrouping is basically breaking the boundaries and optimize them together. By doing that, it can actually optimize for timing and area. So Genus by default it will ungroup user hierarchies to optimize for both time and area. By default, Genus will do auto ungrouping. So for example, I have two hierarchies here. Okay. Hey, look at that. They actually, the two hierarchies, they are using the same input A, B, C, D, and then A, B, C, D. So actually, they can break the boundary and then optimize them together. So you can see left and right. Left side, a lot of gates. Right side, lesser gates. This is called ungrouping. Okay. Once they do ungrouping, they can do a lot of transformations like logic sharing, Boolean optimization, redundancy removal. All these engines will start to kick in to optimize your design. So auto ungroup is something that is very important for the tool to meet your PPA. Okay, remember performance, power, and area. Okay, next is the don't touch concept. Don't touch concept. You need to track any preserve or don't touch that you may have in your scripts. Okay, don't touch is a very easy concept. Don't touch basically means that I might have something in the RTL that I don't want the tool to touch. Okay, there might be a signal net that I don't want the tool to touch. I don't want to do buffering. I don't want you to do, I just want you to retain it as it is. Okay, you can do that sometimes because you probably don't want the tool to, like for example, right? You see the tool does a lot of transformations and techniques to optimize your design, but you might not want to touch. You might want to retain this, right? So you do the set don't touch command to make sure Genius don't touch it. Just leave it as it is. Whatever is in the RTL, just leave it as it is. Don't touch it. Okay. So some set don't touch is an intentionally constraint. Okay, it's intentionally one. So if it's better if you don't have any intention to don't touch anything, so it's better to leave to let the tool optimize everything. Better not to apply any don't touch in your scripts. Okay, the next concept is boundary optimization. Okay, do not disable boundary optimization. Also similar like ungrouping. Okay, boundary opto, the Genius tool will do boundary optimization, which is the process of performing optimization across hierarchy boundaries. Okay, this is where they are optimizing something, knowing that the other hierarchy has some information to help with the optimization. For example, propagate constants. Okay, propagate constants 0 or 1. Okay, for example, for this particular hierarchy, this flop has a logic 0 external of the boundary. Okay, actually, right, what we can do, Genius can actually bring the logic 0 inside, right, and optimize the logic inside. Okay, they can do obvious objects. Similar as this case, this logic 0 is in another hierarchy. The tool will not touch it. The tool must maintain the tool. Okay, sorry, maybe let me retract. Okay, this logic has some logic 0 that is being tied to 0 in another hierarchy. So they can actually bring the logic 0 into the logics hierarchy and then do optimization. Okay, this is what we mean by boundary optimization. So Genius tool will do this kind of optimization to optimize your design. So don't worry, let's say you're coding an RTL, right? You code an RTL and then you define some signal, and then actually the signal is tied to 0 in another module, right? You don't need to pull it over. You can Genius will help you to optimize this. Will help you to bring the logic 0 all the way down to the logic. Okay, they will help you to do boundary optimization. Okay, the next concept is sequential removal. Do not disable sequential removal. Also, another thing that helps to optimize your netlist. You might have some flops that are not contributing to the output signal generation. In other words, redundant flops or constant 0 or constant 1 flops. So we have this command called the optimize constant 0 or 1 flops. So by default, it is turned on. Genius will remove all the flops that are not contributing to the output signal generation. So if a flop may be seen as constant, they can be replaced by a logic 0 or 1. Okay, once the tool replaces your flop, right, then the tool can further optimize further on your netlist. Okay, so that is the benefit of this switch. Okay, some flops may also be just there and not used at all. So some of the redundant flops, Genius will also remove them. So these are all the optimization that's being done by Genius to optimize your netlist. Besides removing your flops, they also do sequential merging. Okay, also do not disable sequential merging. So sequential merging is also another concept which Genius does. It's controlled by this switch called optimize merge flops. So if Genius identifies 2 flops, okay, in the same hierarchy. They see two flops in the same hierarchy, always storing the same value and output the same value. Then Genus will merge them into one element. So this is a very good method to optimize area and also timing. Okay, because from two flops now it become one flop, so you are saving on area. Okay, and also be good on timing. You have lesser timing paths to fix. Okay, next concept is clock gating. Okay, LP insert clock gating is a switch to turn on the clock gating insertion. Okay, so by default, Genus don't do clock gating. Okay, you have to turn it on. You should turn it on very, very early during the read RTL stage. Okay, you should turn it on. Once you turn it on, right, it will enable Genus to move part of the logic from the data cone to the clock enable cone. So it will create a clock gate. It will infer a clock gate for you for some of the flops that has this getting information in the RTL. Okay, so this is how you, this is the switch to create clock gates in your netlist. Next concept is the library cells choice concept. It says here, keep the biggest, fastest leap cell for most critical path. Okay, so just now I did mention about don't use much earlier on when we talk about reading of the libraries. Okay, if there are some library cells which you think are not good for timing, right? Which you think is detrimental to your design. Definitely detrimental one. No good for timing, no good for power, no good for area. Definitely detrimental one. So you can do a set don't use. When you set a don't use on that library, right, on the library cell, Genus will not use it. Will not use it. Okay, there's another one where we call the op high effort deep cells. This is also another concept. Okay? What it does is that there might be some cells which you only want to use it for the most critical path. Okay, for example, there are like some buffers that can drive very high fan out. These are some buffers that are very fast, some AND gates that are very, very fast, right? But they are not good for power, but they're just very fast and good for timing critical paths. Then you might want to define them as op high effort deep cells. So when it sees that cell, right, so Genus will only use it, for the most critical path, not the more critical path, but for the most critical paths. So that is how you control the library cell usage. One is you don't want to use it at all. The other one is you only want to use it for the most critical timing paths. Okay, the last concept, there are actually a lot of concepts, but I feel these are the important ones for Genus synthesis runs. The last concept here I want to talk about is the power optimization run. Okay, the power optimization effort. Okay, so design power effort. This controls how you optimize for power. Okay, this is the main switch to control the power optimization. So none is if you disable power optimization. Low is you perform some optimization. We do not trade off power. Do not trade off delay, area, and runtime. And high is where it performs very, very aggressive power optimization with higher trade-off. So if you enable it to high, right, you might see some timing degradation or area increase and also maybe longer runtime. Okay, so we talk about apply optimization directives. Next, I'll go through. Okay, so this is the test your understanding part. First is one question is how can I tighten constraints by a particular value on all paths through a specific adder? Okay, how do I tighten constraints for a particular path for a particular value? Okay, tighten constraints on a specific adder on all paths. Sorry, let me rephrase. How do I tighten constraints by a particular value on all paths through a specific adder? Any paths through a specific adder. How do I do that? You can use the set path adjust command. So what we need to do is we need to add a delay of 100 picoseconds to and all the paths that goes through a specific adder. So you're actually making the timing path more pessimistic. Okay, some true and false questions. By default, Genus will do auto ungrouping. Is it true or false? Genus, will it do an auto ungrouping? Yes, true, correct. Yes, Genus will do auto ungrouping. And remember, auto ungrouping is basically ungrouping hierarchies so that the tool can optimize it for logic sharing and redundancy removal and so forth. Okay, thanks for the answer, Chang Tiong and Nguyen. Next question is, can sequential merging happen across hierarchies? Can Wilginus go and merge two flops? Although they store the same value, they output the same value, but they belong to the different hierarchies. Can sequential merging happen across hierarchies? Okay, yeah, thanks for the answer. Actually, the answer is no. The two will not merge flops that belongs to different hierarchies. Okay, no, sequential merging only combines equivalent flops found in the same hierarchy. Only within the same hierarchy it will do sequential merging. Okay. Okay, next question. Over constraining the design will increase design area. Increase area. Do you think this is true or false? Over constrain the design means I'm making the slew requirement much tighter. All my logic gates must meet 20 picoseconds transition, right? Or I over constrain by saying I only want my logic gate to fan out to fan out to 10 fan outs. Over constrain means make the design more pessimistic. Do you think it will increase area? Okay, thanks for the question. I do see mostly false. Anyone has an answer for true? Yeah. Okay, yes, that's right. Actually, the correct answer is true. Over constrained design will definitely increase increase area. Increase area. Okay, it will increase area because if I over constrained design means I'm tightening all my constraints. I'm making them meet requirements much tighter requirements. I need to make sure they meet 10 picoseconds slew. Originally, I only can meet 50, but now I want to make sure all of them meets 10 picoseconds. That means the tool must use bigger logic gates, right? Then I say that I want my fan out to be, instead of 32, I want to over constrain it to 10, right? I only allow 10 fan outs only. That means I must use bigger logic gates. Then I must use, everything must be bigger. All my logic gates all are bigger. So it will definitely increase it. So just be careful when you are working on synthesis. If you suddenly see a large increase in area, right, you need to check whether your constraints over constrained. Okay, that's one thing to check. Okay, thanks for your answers. Okay, we'll move on to next part, which is synthesis of design. Okay, so you already apply the optimization directives. So the next thing is how to synthesize the design. Okay, as you know, synthesis is a process of transforming RTL design to gate level analysis. So there are three main commands to do synthesis. The first command is called syngenerate, which is called generate optimization. Second one is synmap, and third one is synop. So you're going to hear a lot about syngenerate, synmap, synop. Okay, I'll describe more in the next slide. So the first command to run synthesis, where the tool is going to start working to optimize your design, the tool is going to start working already, right, is syngenerate. This is called generate optimization. So it is a technology-independent optimization. Okay, technology-independent means it has not looked into your library cells yet. Okay, basically it is mostly doing RTL optimization. Okay, remember I talked about all the ungroupings, all the architecture selection and all those things I talked about earlier on. Yeah, so that is where syngenerate is doing. That's what syngenerate is doing. It will do RTL optimization by doing data path structuring. You will do analytical optimization. It will look at the data paths, look at how critical the timing paths is. Then it will select the architecture, select the appropriate architecture. Do you need fast adders? Okay, or do you need slow adders? Do you need fast adders for the timing critical path and lower power adders for the low power part of your design? Okay, that's where architecture selection is. And then sharing and speculation to reduce area to optimize the logics, and then carry safe arithmetic. All this data path structuring is done during this syngenerate stage. Then it also does constant propagation. Whether once constant propagation is done, whether can it do any ungrouping, can it do any boundary optimization? Then you will try to identify registers to do clock gating. A lot of restructuring. Basically, most of the structuring, architecture selection, data path optimization, all is being done at this stage here. ungrouping of the data path, and chipware also being done. Chipware ungrouping is also done. So chipware selection, all these things are being done with SynGeneric. It has not it has not selecting your AND gates or gates yet. It is just selecting the best architecture for your RTL. Okay. So at this stage here, your design is not in a gate level netlist format yet. It is actually in a they're actually in generic components format, which is the two internal format. It is still in a non-technology format. Okay, it is still based on architecture components format. Okay, and then that's why the next step we call it a SynMap. Okay, SynMap. Okay, SynMap is where we start to do technology-dependent optimization, where we call it as technology mapping. Now they start to map your architecture, your data path structures to the logic gates that is being read in your library. All those libraries that you read in for 1 volt, 0.8 volt, all those, they will start to map the architecture to the logic gates. So the gates will be selected from the technology libraries to implement the circuit. Okay, once they are mapped to the logic gates, then they will do a global restructuring. They will still do some logic optimization, do the Karnaugh map kind of optimization, see whether they can optimize an AND gate, OR gate to some other complex gates and so forth. So that's where they'll do all this technology mapping optimization. And then global net drive optimization, you make sure whether the logic gate can drive this particular transition requirement, this particular capacitance requirement, and then whether are you meeting the fan-out requirements. And then final global timing tuning. So the result of this SynMap is a technology map netlist, where you will use the fastest gates along critical paths and use area efficient gates on the non-critical paths. Okay, this is about the mapping stage, where how it selects the libraries according to the architecture selection that is done during SynGeneric. And then lastly, one more round of optimization. Let's just do one more round of incremental optimization after the mapping, that we call it a SynOp. Okay, one more round of optimization. So what you just do is you improve. Okay, what it does is it will improve the timing, improve area and power, and will fix the DRC violations, let's say transition requirements, capacitance requirements, fan-out requirements. You will start to do timing, area, and power improvements. That is done on SynOp. So the result is a final incremental op netlist. Final netlist. Okay, so yeah, very interesting. So 3 main commands to do the synthesis: SynGeneric, SynMap, and SynOp. And yeah, there are multiple efforts. You can control the effort, whether what is the effort level for generic, what's the effort level for map, what's the effort level for whether you want low, medium, or high. Of course, if you do high, it's usually for those data path intensive designs or designs that are hard to meet time. But take note that if you are setting to high, right, the runtime will also increase because tool will spend more time to do the optimization. Okay, so I'll just quickly go through this on the test your understanding part. So complete the synthesis breakdown. What happens after SynGeneric? What's the correct command to apply after SynGeneric? SynMap, yes, very good. Yes, I believe everybody got the right answer. SynMap, correct. So SynMap is the correct answer. And next question, a true or false question. An optimization technique is considered generic when the technique has no connection to library. No connection to library. So the optimization technique is called generic. Is it true or false? Okay, if the optimization technique has no connection to the library components, is it a generic optimization? Yes, true, correct. Long, yes, thanks for the answer. Correct. Chapo, Nguyen, yes, thank you. Look, yes, thanks. Yeah, those are all correct answers, correct. True. So just take note now, when you are at the SynGeneric stage, it is a technology independent optimization, and it is focusing on RTL optimization. It is not a mapping optimization stage. Okay, quickly, we will go through the reporting stage. So of course, these are all the commands. If you want to know about area, you do a report area. If you want to know about power, do report power. You want to do a timing, report timing. So these are all pretty generic kind of reporting steps that you all must do after you complete your synthesis. Okay, and then once it's done, what do we do? Right, you do the reporting already. Now you have to write out the outputs. So these are the commands to write out the outputs. First one is write DB. So write DB basically is to write a design to a database file. If this DB is like binary format DB, it contains all your design information, it contains all the constraints, everything that you've loaded up into your Genus is stored in the DB in the binary format. So let's say you want to read back the DB, you just do a read DB command in Genus. Okay, and then if you want to write out the netlist in text format, you do a write netlist. If you want to read back the netlist, you just do a read HDR. Remember, we talked about this command at the very early stage. When we say, how do you read the RTL? Use the read HDR. If you want to read a gate level netlist, you can also use the read HDR command. Same thing. Okay. Now, write script is another command to generate the Genus constraints file. All those constraint files that you have sourced in, set max trans, path adjust, path groups, all these constraints that you've done, right? You can write it out using a write script command. And then you want to read back the script, you just do a source constraint file. And then write SDC, same thing. You can write out the SDC constraints file. You want to read back, you just do read SDC. Okay, remember we talked about this, right? Okay, the main takeaway here I want to tell you is that you can do a write command or a report command at any stage of synthesis. You don't have to do it right at the end. Okay, you can do it at any stage. You can do it right after in design, right after read RTL, right after any stage, right after you set the constraints. You also can do a write or do a report. And you can do it after scene generate. Also, you can do it after scene map. Not necessarily need to do it at scene op. You can just do it after scene generate, right? This allows you to do checkpoint analysis at different stages. You don't need to wait until the end to do the report. You can just do at any stage, and then you do a checkpoint analysis. You check, okay, is everything okay? Like for example, you write out the constraints, right? You set some constraints. Then you want to check whether everything correct. You do a reporting, and then you see, oh, actually my constraints are working. Okay. How am I doing on time? Okay. I might be eating into the Q&A session. So I hope you all don't mind, but I'll try to finish as soon as possible. Okay, the next part, I want to talk about the timing reports and analysis, because I saw some of your feedback from the first session. You want to know some learnings, right? So I try to put it into these slides for this session. Okay, so these are just some very simple, very simple kind of analysis of reports. So the first one I want to talk about is the timing report. When you do the report timing, right, you will see this timing report that's being generated. You will see a header. Okay, the header will show you your design name, your operating condition, okay, and then your interconnect mode and error mode. So you look at the error mode is physical library. So you are actually in the PLE mode. Okay, physical layer estimation mode. And then in this timing report, you can see there's a path one. So this is just the first path. Okay, the first path, and then it contains the timing slack calculation. It just tells you your slack 0. Slack 0 basically means you are meeting timing. Okay, this path is meeting timing. And what is this path? This path is actually from a flop start point called select op a reg 0 to an end point called ACC reg 30D. Okay, it's from this flop to this flop. It's a reg to reg path. But for this case, they did not create a path group for it. They actually used the default path group by Genus. Remember, the default path group for Genus is clocks. So you can see the group here is actually a clock name. So means for this particular timing, for this particular Genus run, they did not override the path group. Okay, so they're just using the default group created by Genus, which is per clock basis. And then you can see the capture clock is 8,000. This means 8,000 picoseconds of the clock period. And here you can see the table shows the arrival time calculation. So you can see the delay taken from this arc CK to Q arc is 409 picoseconds. The delay taken for the next instance is 295, and delay taken for next instance is 397. Okay, there's actually a lot of information here. So this one is the name of the instances. These are your logic gates. Logic gates. So is this a scene generate or scene map netlist? This is a scene map netlist because it has already been mapped to a library instance, library cell. So this is an AND gate, this is a AOI gate, maybe it's an AND/OR gate or something. And each of these gates, they have different delays, they have different loads, they have different fan out. This one fan out to 4, this one fan out to 8, this one fan out to 1. They have different slew. slew output, okay, and different delay. And this is just accumulation. 783 actually 409 plus 294. It's just the arrival time. So it's an addition of all the delays. Okay, there is a flag table here to show. Let's say if you do a C, it means it's inside a congested area region. I means ideal net, preserve means P means P. When you see a P means somehow or rather some in part of your scripts there's a don't touch being applied, so you must check. By the way, if you have any questions, please submit to the Q&A box. Okay, this is just another similar report, timing report. So same thing, header has your tool name, your design name, your operating condition, and then your clock period 8,000 picoseconds. And then this time it is violating 200 picoseconds. Now your slack is a negative value. That's why it says here violated. Your path is now violated by 200 picoseconds. Why did it suddenly violate 200 picoseconds? It's because I have tightened the path. I have tightened the path using a set path adjust by 200 picoseconds. I have tightened it. I want the tool to work harder. I have tightened it by 200 picoseconds. So now it violates 200. And now the tool, the tool has to decide I might probably have to use a bigger gate for this. I cannot 294 and 397 is too big. I need to reduce the delay, and I probably need to use a bigger gate, or I probably need to add a buffer. If you can see here, the slew here is very large, 629 the transition. So it's probably a very long from an AND gate to the AY is probably very long. Okay, so the tool estimated to be a very long net. That's why the slew is very large. So they might probably have to add buffer to meet this timing. So you can see here by just changing some constraint, right? It causes a violation, and now tool has to decide to optimize it. They have to optimize it. They have to optimize it either by sizing, mapping, selecting a better logic cell, or maybe do some ungrouping, optimize it further instead of using AOI, maybe use some other type of logics, some logic structuring and so forth. So just one constraint update can cause a change in result, and the change in result cause the tool to use another strategy to do optimization. Yeah. Okay, so just add on, when you're looking at a timing report, find negative slack. Look for paths that are violating. So this is violating by negative 1939 picoseconds. That's large, because your clock period is only 2400. You're already violating 19309. This is large violation. So find paths with negative slack. Find large cell delays. Let's see. I have large cell delays. I have 215 is large. 206 is large. These are cells that are potentially can be further optimized, right? Then find paths that are crossing hierarchies, boundaries. If you see any path here you don't see anything crossing hierarchies. They all seem to be one flattened hierarchy. But if you see anything crossing hierarchies, you might want to check why the tool is not doing any ungrouping. Okay. And then find any cells which are set as don't touch. If there's a don't touch here, you might want to know why it's being set as don't touch. If there's a don't touch, right, tool cannot do anything. If you are setting a don't touch on a M8M, all right, tool will always stick it to an 8M. You will never going to upsize it. You will never downsize it. And so this is going to be bad if you want the tool to upsize it to a bigger cell. And then analyze the critical paths for each path group. You need to create path groups. Path groups is a good way to optimize. Optimize according to register to register, and then set a weight for it. Optimize according to flop to memories. Okay, then set a weight to it. Otherwise, the tool is just going to do a default optimization by clocks. Okay, is there any missing constraint? Is the clock period wrong? You also need to check whether do I really need to meet 2,400 picoseconds clock? Do I need to meet it? Is my clock period wrong? Am I missing any constraints? Missing multi-cycle path and so forth. Okay. Okay, next one is there's another command called report gates. Report gates is another command that lets you view the gates that are being used in your design, library cells. So you can see here in this gate report, it will give you information on what are the gates from each library that's being used. So 4 add gates been used, 1 XOR has been used from this library, 2 memories are being used from here, and the total area is this much. And then furthermore summaries, like for example, how many instances used from each library, and then details about instance group. Okay, this is about instance group. So how many flops in your design? how many buffers, how many inverters, how many combi logics, and how much area. Looks like most of the area is being used by timing model. Timing model is like a black box, a timing black box. It can be your memories, macros, those sort of things. Largest area, 73% is being used by SRAM. 18% is used by combi logics. Wow, there are a lot of combi logics in this design. And only 7.5 used by flops. Not many flops in this design, a lot of combi logic. So it looks like a very data intensive design. A lot of combi logics, only a few flops. So this probably means that from one flop to another flop, there could be many logics in between, and it can be bad for timing. So you need to check from this report, are there certain flops not selected? Are there any flops that are not selected? Review your don't use list. Are the number of black box listed correctly? Are the number of SRAMs correct? Are there too many buffers and inverters? Too many buffers and inverters can mean that your transition requirement is too strict, right? So you have to use a lot of buffers, right? So you need to review these kind of things. Okay, area optimization help. If you need some help with area optimization, check that Genus is not fixing transition requirements aggressively. Are you over constraining your design? Double check your constraints. Then remove and review any preserved don't touch attributes that are not needed. Okay. And are you enabling auto ungroup? Remember, auto ungroup optimizes for both timing and area. Next one, timing optimization help. We recommend you to do a detailed analysis of timing report before you run your synthesis. So make sure before you run your syn generate, because syn generate, syn map, syn op is going to take some time. So instead, why don't you, before you do that, right, before you run synthesis, why don't you just do a timing report? Just invoke a report timing and find out what's the timing quality before you run synthesis. Whether are you seeing huge delays or are your constraints correct? Or maybe your clock period is too pessimistic and you have like 10,000 or 1 million violations because your clock period doesn't make sense, right? So just remember to do one round of timing report before you run synthesis. And then create cost groups for IO paths. IO path violations are large. You don't want them to be optimized together with other paths. So you want to create another path group for IO paths. Separate them. Let the tool optimize it as a separate group, separate cost group. Are you choosing the right library cells for synthesis, right? So low VT cells can improve timing significantly, but it will increase the leakage power. So some cells, they are good for timing, but they can be bad for power. Some cells good for power, but bad for timing. So you have to choose the correct library cells for synthesis. Decide on what are the library cells that you want the tool to use. Even though you load in 8 libraries, and then you can also selectively set certain library cells that you don't want to use using the don't use command. And then are you enabling auto ungroup and ensure you are using QRC files to increase the accuracy of validity. QRC files, remember I talked about it, is part of the physical layout estimation. You want to increase the correlation to the physical phase. You don't want to have any surprises. You don't want like synthesis is clean, everything is very good. When you go to the physical phase, all my violations will pop up. You don't want that. You want to have some sort of correlation. Whatever timing violation you're seeing in synthesis, you're also seeing the same thing in physical phase. Okay, and then just to take note that you might want to have like some names. You might want to override some of the naming convention that's being used by Genius. Like for example, you might have some instance name that has this add 83, and then you don't like this kind of Genius naming convention. You want to change all these underscore to 2 double dash. You can use the update names command. So the new name will be in such a way, then it will also appear in your output netlist. So you can use the update names command to override the names of instances. Okay, update names command let you change the name of select objects such as names, buses, and instances. Okay, so that's all on synthesis, logical synthesis. Okay. I will now talk a bit about physical synthesis, just very briefly about physical synthesis. Okay, so when we talk about physical synthesis, we have to use the word iSpatial. Okay, iSpecial is our Genus next generation common physical optimization flow. Okay, so you just see, if you from this diagram, it has a very accurate representation. So the old flow, the one that I've been talking for the past 1 hour, is actually the old flow, where you are running a scene generate, scene map, and then you just do scene op, and then you transfer this DB to InnoOS to do optimization, place optimization. iSpecial is where you are bringing it's quite similar, but instead of an incremental optimization in Genus, you are actually bringing part of the InnoOS place of designer into Genus. Okay, you're doing, so that's why it says that the first part of place of design is done in Genus. You're bringing this InnoOS place of design engine into Genus to do a early physical optimization. And then you just transfer this DB to InnoOS to continue to do the incremental place of optimization. So the Genus iSpecial flow is very similar to the conventional logical synthesis flow. Basically, there's just additional iSpecial setup, additional of a read floor plan depth, and then you need to use these commands like scene generate. You need to add a dash physical there, dash physical option for scene map, and then scene op is no longer just scene op; it's actually scene op dash special. Okay, and then after that, finally, you can just write the DB and transfer the DB directly to InnoOS. So just take note that the Genus physical license is required to run iSpecial. Okay, the Genus iSpecial setup, you just need to have this as some extra settings here. Okay, the main setting I just highlight here is actually the InnoOS executable. You need to tell Genus which InnoOS executable, which InnoOS tool version to be used for this iSpecial. You need to provide this option here. Okay, to run iSpecial flow in Genus, you need to set certain attributes to configure the flow. Okay, and then of course, the most important thing is your inputs, right? If you want to run iSpecial flow, you need to make sure you also have the correct physical inputs to do this physical synthesis. Okay, so that is why here I'll talk about you need to read your left. Okay, no problem, right? Because even in logical synthesis, you need to read the left for PLE, but it's also very important for you if you want to run Genus iSpecial. The next important file that you need to read in is your floor plan depth. This is an example of a floor plan depth. Okay, you use the command to read your floor plan depth is the command read depth. Okay, the read depth file name is the command to read your floor plan depth. So for iSpecial, you need to read in your left files, your QRC tag files, and your floor plan depth. Okay, so here, same thing. Everything is exactly the same, okay? Like what I mentioned, ungrouping, auto ungrouping, boundary optimization, all the concepts still holds true for Genus iSpecial because we are still using the scene generate and scene map engine to do the synthesis. We're still using the same generate and map engine. So everything that we talk about, it still holds true. And I'll just add on top on the options that need to be used with your Genus iSpecial. The additional options for scene generate is scene generate dash physical, where you will remember at that generic phase you are still in generic cell format, okay, the non-library format. But if you add a dash physical, it will use the physical information. What's the physical information? The floor plan depth, the left files. It will use this information to try to do cluster placement of your generic cells. Placement on what? Okay, placement on your floor plan depth. You will try to place your generic components on the floor plan depth. Okay, then scene map physical, exactly the same. Scene map is also about mapping to logic libraries. But this time, if you add the dash physical, it will use the physical information more. It now knows the placement from the floor plan depth. It now knows that your memories are placed here and your register is placed here. It now knows that it's a very long path. So it uses this information to select a better logic library, a better cell library for mapping. Maybe it needs, last time it was using small buffers. Now, because it's so far away, it needs to use a bigger buffer. And last one, scene op spatial. Scene op spatial is no longer just about incremental optimization. Okay, remember SynOp, we talk about, it's about improving timing, right? SynOp Spatial is now a situation where you are using the iSpatial engine. You are using the Innovus executable within Genus. Remember, we defined the Innovus executable, and it enables a unified physical optimization. What do you mean by unified? Unified means I'm uniting both Genus and Innovus engine together. I'm uniting both of them together to do physical optimization. The engine is actually a physical restructuring engine where it does placement. Placement. Why it can do placement? Because I got a floor plan, so I can do placement. And then where placement together with physical optimization, which tool to do the physical optimization and placement is Innovus. And then it used Genus engine to do large scale logic restructuring. Remember, Genus is all about restructuring logic, restructuring components, and so forth. So now I'm unifying two engines together to do this SynOp-spatial. Okay, so that is what we mean by unified physical optimization. So reporting exactly the same. Report QR, report area, all same information. Okay, so the timing information after iSpatial now is more accurate because it is based on accurate extraction data from Innovus. The key takeaway here is that we are improving the correlation to the physical phase through this unified physical optimization algorithm. And then this is just a GUI. Okay, I didn't talk about GUI here because I'll focus more on the information related to non-GUI part. So basically, this is just a GUI to show you can see the congestion map here. You can see the congestion map very early on if you're doing Genus iSpatial. Otherwise, you have to wait to the physical phase to see the congestion map. Okay, finally, okay, so everything is the same, right? And then you know the benefit of the unified physical optimization. Then lastly is how do we hand off from Genus? How do we hand off from Genus? Okay, so you already completed. In the old flow, you only can pass the netlist to Innovus. But in the new flow, you got two options. You can use the netlist handoff flow, or you can use the DB handoff flow. The netlist handoff flow is basically similar. You just write the netlist and then you pass it on to Innovus. Or you also can do the DB handoff flow. Okay, the DB handoff flow is where once Genus SynOp iSpatial completes, you can do a write DB. Okay, you can do a write DB, and this DB that is written now is actually done by Innovus. So this means that this DB can be read directly by Innovus. Okay, that is why we are seeing like 30% faster runtime. Okay, because this DB you can just pass it on from Genus. This Genus can write out a DB that can be read in by Innovus, and once Innovus reads in this DB, right, the design is already half placed. So it does not do to do placement all over again. You can just do an incremental place. Okay. By the way, if you have any questions, please submit to the Q&A box. Like if I'm not clear on the if my description is not clear on the benefits of the iSpatial, do type questions in the Q&A box. Okay, this one I won't talk about. All right, so test your understanding part. Identify the missing pieces of this iSpatial flow. So what happens after the global variable and attribute settings? What comes before the library and MMC settings? For iSpatial, what is the step here? What is the extra step that we need, extra setup step that we need to do for if you're going to run iSpatial? Oh, Chavo, very good. Yeah, that's exactly the answer. Yes, iSpatial setup. Very good. Good, thanks for the answer as well. Yeah, you all got the answer correct. Yes, it's iSpatial setup. And then what it comes before SynMap physical? And then what comes after SynMap physical? Yeah, what are the two steps? What is the step before SynMap physical and what's the step after SynMap physical? Yes, Jiang, good, correct. Yes, correct. SynGenerate physical is the step before SynMap physical. You need to add the dash physical option, and SynOp spatial is the command to invoke the iSpatial. Not SynOp, it's SynOp spatial. Remember, if we do the synop spatial, we will invoke the innovers executable to do the unified physical optimization. Okay, physical oops, I given the answer. Sorry about that. Okay, so physical synthesis requires floor plan information through a dev file. Dev file, you must have the floor plan dev. Otherwise, how is Genus or Innovus going to do the placement? Right? It needs the dev file. Okay, what benefits should we expect to see with Genus iSpatial? What benefits do you expect to see with Genus iSpatial? What benefits? Faster, yes, correct. Faster is one of the benefits. Chang Kyong, correct. Faster because you can easily pass on the DB, right, to Innovus. Innovus can read it and it doesn't need to do a full placement again. You can just do incremental placement because most of the placement is already done. Most of the global placement, remember you talked about global placement in the first session, first stage, right? Most of the global placement is already done during iSpatial. Okay, there's also another benefit, and that benefit is predictability of pre-CDS timing. Predictability. You meaning to say at Genus stage, if you have the synop spatial done already, right? You can now know how it will look like at the physical phase. Okay, you will have some sort of degree of predictability of the physical phase when you are running Genus. And then better PPA. Why better PPA? Better PPA because we have now a unified physical optimization. We are now combining both logic restructuring and physical optimization together at synop spatial. So that is the benefit of this flow. Okay, very good. Thanks for the answers. Okay, yeah, we are finishing. So this last few slides is just to briefly talk about some other somehow related to Genus, but it's some sort of like additional topics. So for instance, DFT flow. DFT flow can also be done by Genus, and it's also done part of the logical synthesis. The only additional things that needs to be done is you need to set up the DFT rule checker. Okay, Genus can also help you to fix the DFT rule violations, add the testability logics, and then SynMap, SynGenerate all will help you to do the scan connections. And then after the scan connections are all done, all the scan mapping and so forth are all done, scan stitching is all done and so forth, right? You can run a synop or synop spatial to optimize your netlist that contains DFT information. So this is how you optimize not only your functional constraints, you also can optimize based on your DFT constraints if you do your DFT insertion Genus. Okay, so majority of the optimization directives, everything are all the same in Legend MMC file, everything the same. Just some additional rule definitions, scan chain configurations that needs to be added on. And even when you write out, you don't need to write out netlist. You can also write out the ATBG, write out the scanf. So everything can also be written out by Genus. Okay, the other last few slides is about the formal verification. Okay, this formal verification, I have to mention it because it is one of the most important verification steps after you have completed synthesis. So this picture is actually from your first stage. Basically, we only talk about here, okay? But in this slide, I also want to talk about this part here, the formal verification. The formal verification is used to do a logic equivalence checking, okay? Is to check the logic equivalence of your synthesis netlist versus your RTL. Okay? You need to make sure that whatever has been synthesized outright matches the functionality of your RTL. Okay, that is the formal verification that needs to be done. So the conformal LEC is a formal verification tool that can be used to verify the functional correctness of netlist synthesized by Genus. So Genus, in the Cadence flow, right, we use the conformal LEC tool to verify the functional equivalence between the Genus and the RTL. Why we need to do that? Because synthesis involves a lot of complex optimization and transformation. Remember architecture selection, ungrouping, boundary optimization, logic sharings, all these transformations and complex optimizations right, need to be checked and make sure that they are done correctly without violating the functionality of the RTL. So that is why this formal verification must be done. So it is strongly recommended to perform functional verification after synthesis. So here I'll just show you a very brief flow on how to do this formal verification. No, sorry. Actually, I'm not showing the formal verification steps. I'm showing the flow of how Genus writes out the scripts that is needed by LEC to run the formal verification. So this one is more of like how does Genus prepare the files for formal verification to be done by LEC. Basically, it's like a handshake. It's a handshake flow. So you can notice here that right after SynMap, you can start to do LEC verification, right? Because right after SynMap, there's one every map information will be written out automatically to the verification directory. So then you can just do a write do LEC and then this command, and then write it to a tickle file. Okay, write it to a tickle file, and then this tickle file can be read in by the conformer tool to do functional verification. So the formal verification that is being done here is between RTL against this every map, which is part of your checkpoint after SynMap. Okay, so you use this formal verification check between your RTL and your every map database. Okay, then if you want to continue on, right after SynOp, you can do another write do LEC command, and then it will write out a tickle file, which every map to final tickle. So this can also be read in by the conformer tool. So it's a script that can be used by LEC to compare the final netlist, the final V, against the every map, So the first stage, this is some sort of like a two-step LEC. First step is to compare RTL to the every map. Make sure it's passing. It has to pass. Once it's passing, then next step you can check is between the final V and the every map. Okay, so that is the two-step formal verification flow handshake that can be generated by Genus. Okay, I hope this is clear. So in Genus, use the write do LEC command to generate a script that conformer LEC can run to verify the netlist. Okay, last one. What is the verification name and cadence tool used to ensure that the synthesized netlist is functionally equivalent to the original RTL design? Yeah, okay, this is one just mentioned. So I'll just quickly go through this one. So this one, the answer is formal verification using the conformer LEC tool. Yes, correct. Yes, formal verification, correct. And the tool is conformer LEC. And how Genus prepares the script is you can just do the write do LEC command. Okay. And then yeah, just some help. If you need help on the commands, you can look at the documents, or you can also do the help commands to do it. Basically, just do the help star or help command name, and it will give you information on how to use the commands. Okay, so that's all. That's all the topics that I would like to discuss on this stage 1-2, which is the Cadence digital front-end design logic synthesis using Genus. Okay, so now I'll open up for Q&A. So if you have any Q&A, please type it into the Q&A box, and I will try to answer it together with the expert panelists, Vian and Hui. I see there's one question in the chat box much earlier. Let me just double check. There's one question about MMC file, if I'm not mistaken. It's really okay. So the question is, if let me see, if we read the MMC file at Genus, do we still need to read the MMC file at Novus? Okay, so yes, the answer, yes, you still need to read the MMC file at Novus, because in Genus you are doing one round of read MMC, but to interface to Innovus, right, you need to write. You can only interface it through the right netlist. So you will pass on the right netlist. You will pass on the netlist to Innovus, and when you pass on the netlist to Innovus, they're all in text format. So you have to read back the MMC file in Novus. Okay. So yeah, you need to rewrite the. You can use back the same MMC file, or if you want to add more views, you can rewrite the MMC file again. Okay, but just to add on, if you are doing iSpecial, you might not need to do that because you're passing on a DB. Yeah, it's a good question actually. If you are passing on a DB, right, then you don't need to write the MC file because the MC file is already stored inside the DB. So if you're doing iSpecial, you do not need to rewrite the MC file because it is already saved in the DB, and Innovus will just load the DB as it is. Okay, any other questions? Any questions on like timing optimization, area optimization, or any specific genus recipe or features? Any questions on the inputs or the outputs? Okay. Okay. Yeah, I hope the slides are clear. I might have rushed through on a bit of some of the parts. So if there's anything that is not clear, you can share. You can also ask. Give me a second. I might share. Okay. So Ice.
Yes, student.
Oh wait, I do see a.
Hello, Julian.
Okay. Do you want me to share the? Remember, you wanted me to show the. Yeah.
Can.
Uh, do you have it? You want to show it again? You want to share again?
Sure. Maybe I can
Okay.
share. Wait a minute, because I already closed. Let me
Okay.
reopen it.
Okay. There is a question by Chang Tiong about the training material. So for now, Chang Tiong, we actually for all those sessions, webinar sessions that we have conducted, right? We will take a video. We will have a video recording, and we will put this video recording into the video on demand in the link. There's a link called the video on demand. So you can actually click on that link to view the video again, and then the video, of course, you will see the slides and so forth. So we will not be sending out the training material, but we will be providing this link for the video on demand, where you will be able to see the whole recording of each of the sessions. Okay.
Okay. So Julian, maybe you can stop sharing, then I can share the page.
Okay.
Okay. Thank you. Okay. So I think everyone can see this page, right?
Yes, correct.
Yeah. Okay.
Okay.
Yeah. So for all the candidates, if you didn't receive the last time certificate, please send email to this email address, eventc@cadence.com. I will put this here for around 5 minutes. So Julian.
Okay. Okay, thank you, Ice. Yeah, so this is the, if you don't receive any certificate for the stage 1-1, please reach out to this email address. Okay, so just to let you all know, the next session will be the stage 1-3. We will be talking about INOS, about the physical phase, So the physical phase has placement, clock tree, and routing. So there'll be stage 1, 3, 1, 4, and 1, 5. They will talk about those topics. So the next stage 1-3, which is the placement topic, will be conducted next month. I think it's on the last Wednesday of the month. Okay, so you will be receiving a reminder closer to the date. So those are very interesting topics because there's a lot more optimization engine that is done after synthesis, a lot of physical placements, optimization, and then clock tree and routing. So those are very interesting topics. So we hope that you all can join as well. Okay. Yeah, you're welcome, man. So hope the lecture is clear. And there's a bit of noise from my side. I hope it's not so. Hope you all didn't hear that. Yeah, thanks everyone for attending this, and thanks very much for actively participating, answering the questions and everything. And it is also by way of answering also trigger some discussions, which is very good. It's good to have discussions and share knowledge among each other. Okay. So we might want to end it early since there's no further questions. Ice, is it okay if we end it earlier, Eugene?
Yeah, can. I
Okay.
think I have no concern. So Eugene, is that okay?
Sure. Yeah, it's good. Yeah, thanks everyone.
Okay. Right. So thank you everyone for attending, and hope to see you all for stage 1-3. Lots of interesting information coming up for the next stage. Okay. Right. Thank you everyone. Have a good day.
Thank you.
Bye.
Thank you. Have a good day. Bye-bye.
Bye.